Hi everybody and welcome to a new video in the Generative Music AI course. In the previous tutorial, we implemented a genetic algorithm that could generate a harmonization for a melody. Today, we're going to dive into one of those topics that I've been requested n number of times. That is transformers. Well, not really these transformers, but rather transformers architectures in deep learning. Given the complexity of this topic, I've decided to divide it into two different videos. So today you're going to get part one. In order to make the most out of this lecture, it'd be fantastic if you were familiar with vectors, matrices, and matrix operations. We're talking basically about linear algebra. It's also great if you're familiar with basic notions of deep learning. In case you have no familiarity with the above, no problem. I have a full series on deep learning and linear algebra up here. If you don't have time or you just want to get into this topic straight away, no problem, you can do it, but certain things are going to sound a little bit weird. I'm going to make a quite strong promise to you. That is, if you follow this video and the next, you're going to understand how transformers actually work. The reason is because we're going to get into the nitty-gritty details, theoretical details of transformers, and we're going to also look at the mathematical formalization. So by the end of these two videos, you're really going to understand how they work. Of course, it's going to take some time to get there. So this video, I'm sure, is going to be quite long and it's going to be super involved. So relax, sit on your sofa, make a cup of tea and enjoy the ride. Before we get into it, I just want to reference this amazing book called Getting Started with Google Birds. I've drawn a lot of inspiration for these two lectures regarding transformers from this book. If you want to get deeper into these topics, I highly suggest you check this one out. Without any further ado, let's get into today's video menu. We're going to be diving into a lot of different topics. We're going to look at the context behind transformers first. Then we're going to be looking at the intuition and the architecture of a transformer. Then we're going to be diving deep into the encoder part of the transformer. We're going to look at the encoder block, self-attention, multi-head attention, positional encoding, feedforward layer, adds and norm layer, and finally we're going to revise how an encoder works step by step. I'm sure you may not be familiar with all of these terms, or perhaps with none of these terms, but that's not a problem because I'm going to break them down for you throughout the video. Let's take a time machine and go back to 2015. If you want to analyze or process any type of sequential data problem in 2015, like text in natural language processing or music for music generation, you would probably use a model called an RNN LSTM, so a recurrent neural network or a long short-term memory network. These were all the rage back in the day for analyzing and processing sequential data. The problem, though, is that these models don't have the ability to capture long-term dependencies. And what are these? Well, this means basically that if I want to generate like the next note in a composition, the next note obviously should depend on the history of the composition so far, and it should be able to go back quite a lot in the history in order to create something like that makes sense musically. You need to have those long-term dependencies between all the different items in a sequence. RNNs struggle quite a lot with this. And because of that, in 2017, an amazing paper came out that revolutionized deep learning forever. And that's called Attention is All You Need. This paper presents a couple of things that are just super bangers. Number one, the attention mechanism. And number two, the transformer architecture. This paper is one of the most referenced papers in the history of artificial intelligence. And at the same time, it had an incredible impact on the way we do deep learning today. Transformers are used and everywhere, and they dominate most fields. They are the state of the art for natural language processing, but they've also been extensively used for image processing. They are at the basis of large language models. They're at the basis of a lot of generative AI applications. And lately, they've also been used for generative music. Let me give you a couple of examples of transformers architectures in production settings. ChatGPT, I don't think it needs any introduction. GPT stands for Generative Pre-trained Transformer. So if you follow along these two videos, you're going to be able to understand the basics of how ChatGPT works. Of course, ChatGPT is way more complex, but the vanilla transformer is what is at its heart. ChatGPT is an application for text generation, obviously, but we also have other applications, like for example, MusicLM, developed by Google. It was released a few months back and it generates music in a quite extraordinary manner. Let's take a look at the basic concepts connected with transformer architectures. First, they deal with sequential data. They're able to capture long-term dependencies. They completely get rid of recurrence. Transformers use the self-attention mechanism, and this is what makes the difference. Really, this is where the magic happens. Let me show you the overall architecture of a transformer. Don't be scared. I know it's overly complex. There are a load of moving parts here, but let's pretend they're not there. And we're going to just group this complexity into two blocks. Now, I'm going to invoke the power of the fairy godmother, her magic, and I'm going to use my magic wand, and all of that complexity from those two black boxes is going to disappear. Good. So now we have two high-level black boxes. On the left, we have the so-called encoder. On the right, we have the decoder. Now, this is the core architecture of a transformer. It's an encoder-decoder architecture. What do these things do? Well, let me show you an example of how this works from a very high level perspective. And I'm going to be using the example of language translation. This is the same example that the authors of Attention is All You Need actually used. First step, you feed a sentence to the encoder. This is the sentence that we want to translate. The encoder outputs a representation of the sentence. What is a representation? Well, it's actually an embedding. It's a matrix, as we'll see in a while. It's a rich representation. Okay, then this representation, that's the output of the encoder, is fed to the decoder, and the decoder generates the translation. Let me give you a visual representation of that. We start with this sentence, I like cats. We feed this into the encoder all at once. Then the output is going to be a representation of this initial sentence. It's a rich representation with a lot of context. We feed it into the decoder. The decoder is going to generate the translated sentence, for example, in Spanish, me gustan los gatos. Great. Now, I want to focus only on the encoder side. In the remaining part of this lecture, we're going to be diving into all the complexity and components and subcomponents of the encoder black box. First, let's take a look at the encoder as a whole. As a whole, we can see that the encoder is made up of a number of stacked encoder blocks. Each encoder block does an encoding and passes it over to the next encoder block. Here, I should be super clear regarding nomenclature. The overall thingy here is called an encoder, and I refer to these modules that do the encoding individually as encoder blocks. But given I'm quite lazy, throughout this video and the next, probably I'm going to refer to these encoder blocks directly as encoders, but you should know that there are two levels there. An encoder is made up of many encoder blocks stacked on top of each other. And you can have as many encoders or encoder blocks as you want. The output of one block is the input for the next encoder block. The moment we arrive at the final block, the output will be the representation itself. And this is the representation that then we feed into the decoder. In the paper, attention is all you need. The authors suggested to have 6 encoders. We can have as many encoder blocks as you want. Oh, by the way, you noticed that, right? I mentioned that the author suggested 6 encoders and I wrote that. No, it's 6 encoder blocks. But as I said, I'm going to be using encoder and encoder blocks alternatively. Right, so you may have a question here, and that is, but why stacking encoder blocks? Can't we just have a single encoder block? Isn't that enough? Well, potentially it's good enough, but perhaps you want more. And this is like very similar to what happens with convolutional neural networks. In CNNs, we have a lot of convolutional layers. The more convolutional layers you have, and the more complex representations you're going to be able to generate, passing information through all of those convolutions. And what happens is the same thing with multiple encoder blocks. The deeper you go and the more complex the representation. In particular, different encoder blocks are going to be able to learn different aspects at each layer. And the deeper you go, the more abstract the features that these encoder blocks are going to be able to represent. This is very similar to what happens with convolutional neural networks. The deeper you go in the convolutional layers, the higher level of abstraction you get in terms of the features that they're able to extract. It's a sort of hierarchical extraction of features from least abstract to most abstract. Finally, if you use multiple encoder blocks, you're going to have improved contextualization. What is contextualization in this particular case? Well, it is the ability of having representations where each word knows about all the other words. So it knows the context, it knows all of this relationship between those items. Good. Now, let's dive deep into an encoder block and see what we have, what the different components or subcomponents of an encoder block. So as you can see here, we have 3 subcomponents: the multi-head attention, outer norm, and the feedforward sublayer, and then we repeat outer norm. Each encoder block is always the same. It does this encoding through these 3 sublayers, different sublayers. We're going to be focusing on multi-head attention first, but unfortunately, we can't dive into that until we understand self-attention. It is extremely important that now you devote the most attention you can, no pun intended, to self-attention, because if you do understand self-attention, you basically have the keys to understand any type of transformer architecture, from the least complex to the most complex. This is really where the magic happens. So please devote as much attention as you can to the next section. In order to understand self-attention, I need to introduce the context for that and let you understand the problems that we've had with previous models. And we'll do that with this sentence as an example. My friends like tomatoes because they are tasty. There's some level of ambiguity in this sentence, isn't there? And that has to do with they. We should understand what they points towards. It could be that my friends like tomatoes because my friends are tasty. It really doesn't make much sense, right? But unless you are a cannibal, in that case, I mean, it could make all the sense in the world. But the other interpretation, the right one, would be my friends like tomatoes because because tomatoes are tasty. So I was just like morphing into a cannibal myself, I guess. Okay, so they references tomatoes here. Now, for us, understanding this is quite intuitive. It's something like that we do since we are small children, right? But for a model, it is quite difficult to understand these nuances, and this is where we need that kind of long-term relationships being accounted for. And indeed, we're going to do that with attention. So how can we solve this problem? Well, we want to compute an embedding that not only has information about each word, but about each word in relationship with all the other words, so that it knows the overall context. And we're going to be calling that embedding an attention matrix. That is the self-attention mechanism. Let me give you a visual representation of this, because I'm sure it's going to make things more clear. Here we have our nice little sentence. My friends like tomatoes because they are tasty. And now we get like this they, and we see that we can create a connection with all the other words in the sequence, in the sentence, and the strength of the relationship is represented by the thickness of this line. And as you can see in this case, they is particularly related to tomatoes because the line is super thick. This is attention. In a nutshell, this is the intuition behind attention. We want to understand the relationship of each word with all the other words in the sequence. It's quite simple, isn't it? Yeah, the intuition is simple, but the mathematics behind it is quite complex. And we're going to dive into all of it, but as I mentioned, please do give me your maximum level of attention. Again, no pun intended. So we'll take a look at the protagonist of the self-attention mechanism first. And these are all matrices, and we have 4 matrices. One is the input embedding matrix, I. Then we have the query matrix, key matrix, and value matrix, QKV. I'm not gonna tell you what these represent yet, but we're gonna dive into each one of them when the time is right. And the time is definitely right to dive into the input embedding matrix. The dimension of this matrix is going to be the number of words, and that is the number of rows that we have, by the embedding dimension. And this is something arbitrary. You can put it to 64, 128, or 2, as in our example for simplicity's sake. And each row is going to be a word vector. In other words, each row describes the embedding for a word. It provides all the features, and by feature I mean all the values of the embeddings for that particular word. Here's an example. I like cats. So we get this natural language expression sentence, I like cats, and we convert that into this matrix. You see each row is a word, and here we have the associated embedding values, embedding features for each one of these words. So 0.2, 1.2 for I, for example. So that is the word vector for I. This is a way we use to let the model understand the original sentence. So we convert that into an input embedding matrix like this. This is it for the input embedding matrix. Now let's move on and check out all the 3 other matrices: query, key, and value matrices. And here you have them. They have the same dimensionality as the input embedding matrix, but this is just like by random choice. You could potentially decide to have a different number of embeddings than we had with the input matrix. But usually you would have the same number, the same dimensionality. So in other words, these embeddings would have like the same number of features, the same number of columns. But of course the number of rows is going to be the same, because each row represents a different word for the sentence that we have, or the sequence that we have. Okay. Again, I'm not going to dive deep into the meaning of Q, K, and V yet. This is going to become apparent later. For now, let's just treat them as mathematical constructs. A question you may have is, but where do we actually derive these matrices? And here's where we derive them, from 3 other matrices. Okay. So we multiply the input matrix by 3 weight matrices. So we have I dot products with W, K, Q, and that gives us the query matrix, and you have the same thing for K and for the value matrix. Now, these weight matrices are the ones that we use for training our model. In other words, we learn these weights. When we train a transformer, one of the things that we learn are the weights for WQ, WK, and WV. Okay, but now, all of a sudden, for this damn self-attention mechanism, it turns out that we have 7 matrices. Input matrix, Q, K, V, and then we have the weight matrices for Q, K, and V. It's a lot of things, but why do we need them? Well, the reason is that using these matrices, we can create the relations of a word with all the other words. In order to compute this relationship, we need Q, K, and V. And I'm going to demonstrate you this by showing you the formula for getting the attention matrix Z. Right, it's complex, isn't it? But don't worry, again, we're going to break this one down step by step. So as you can see here, we get a matrix that's called Z. And of course, it's a function of Q, K, and V. And this is like the overall embedding that has that information of each word in relation with all the other words. So that's the promise. And you need this monster formula here to calculate that. Again, this is very complex. We're going to go step by step in the self-attention mechanism. And it turns out that we need 4 different steps. We start from the core, and that's the first step. That is a matrix multiplication between the query matrix and the key matrix, but not the key matrix, it's transpose. So we take the key matrix and we take the K transpose. How do we do this? Well, each row in each column in the original matrix is going to become a row in the relative transpose. This is like how we do the transpose for those of you who are not familiar with matrices. Okay, so now we have the K transpose. So now we can multiply this too. But before we do that, I just want to rewrite a couple of things. And these are this vector here. So I'm going to call this word vector for Q, Q1. And so this is the word vector for I. This is the word vector for the query vector for I. And in this case, I'm going to have this K1, and this is the K vector for I. And if we do this across all the other like rows and columns, we're going to get Q1, Q2, Q3, and K1, K2, K3. Why did I do that? Well, because I want to show you how then we actually going to calculate the multiplication between these 2 matrices. And you'll see that at each cell here, you're going to have a dot product between one Q vector and a K vector. So if we take, for example, the first cell here, the value for the first cell is going to be the dot product between Q1 and K1. So we do this by multiplying this item by this item and summing that with the multiplication between this second item with this second item. This is the formula for the dot product. And so at the end of the day, we're going to get a single value, a scalar. Okay, so if we move one step towards the right in terms of the columns like this, you'll see that here we have the dot product between Q1 and K2. I'm going to give you an example for this other one so you understand. So this is the result of the dot product between Q2 and K3. Okay, so now this is the overall result that we get in the end. This is particularly interesting because you can see that we have I like cats here in the rows, but we have the same thing in the columns as well. And this is square matrix. And whenever we use a dot product like this, what we are actually obtaining is the distance between two elements. Like for example, whenever we do this let's say Q1 by K1, we're going to get like this value here, 2.7. This is the similarity of this Q1 vector and this K1 vector. That is the similarity of the query for I and the key for I. So we can think of that as a distance or a similarity value. And indeed, if we take this value here, for example, we could say, okay, this could be thought of as a similarity score between cats and like. If you abstract that for the entire matrix, you can think of this matrix as sort of similarity score between all the words. So each word, how similar is each word compared to all the other words, right? Good. So this is the meaning of this quite arcane matrix multiplication. But I promised I would tell you more about Q and K and all of these matrices when the time would come. The time has come. So what are Q and K really? Well, we can think of Q as the current item in the sequence that you are processing. This is like something that happens all the time in NLP. So you would process a sequence item by item, and you would call the item that you are processing the query. And let's assume you are the query. As a query, you may ask, what other words in the sequence are relevant to me, and how relevant are they? This is the query. And then we have the key, and the key corresponds to all the items in the sequence that the query can attend to. In other words, this is all the items the query can be in relationship with. Okay, so this is like from an abstract point of view. Now let's try to visualize it like with our old friend, this visual representation. Okay, so we can think of the right-hand side here as the query. In this case, they is the query item. And what is it querying? Well, it is querying all of these keys here, all of these items that obviously coincide with all the words in the original sentence, because they can be connected with any of these words. So this is the deeper meaning of the Q matrix and the K matrix, or the key matrix. Okay, so now we are done with step one. We understand that this is a matrix that represents the overall similarity score, if you will. Then there's step two. Step two is super straightforward. We just divide like that similarity score by that weird thing there, and we'll see what that weird thing is in a second. So we divide KT by the square root of the embedding dimension of K. If you remember, this is K, this is our key matrix. The embedding dimension in this case is equal to 2, because we have 2 features in the embedding. In other words, this is the number of columns that we have. Okay, so let's just apply this step, and this is quite straightforward. So we start with this score similarity matrix that we had here. We calculated this previously, and we divide that by the square root of 2, 2 being the embedding dimension of the K matrix in our case. And this is quite straightforward, because dividing a matrix by a scalar is equal to dividing each cell, each item in the matrix by that particular scalar, like this. It's quite straightforward. Okay, now the question is, but why do we do this? Does it make any sense? Well, it makes sense Because by doing this scaling, because at the end of the day, we're just scaling the values, we're going to obtain gradients that are more stable. And more stable gradients equate to faster convergence and easier training. Okay, step 2 is done. Good. Now on to step 3. Step 3 is basically moving from this guy to this guy. So we have to apply softmax. Why do we do that? Well, so up until now we have a scaled, in this case we have a scaled score or similarity matrix, but of course it's not normalized. We have values all over the place. We want to normalize that because it's just nicer. So what we're going to do is normalize that during step 3. So we normalize the scaled similarity scores applying softmax. What softmax does is it takes each word vector that is a row and it basically normalizes it so that if you add up all the items in the row, you're going to get a value of 1. And that is nice because that is basically a probability associated with each item in the row. So let me show you that. Okay, so here we have the similarity score. We've applied softmax here, and it turns out that we get something like this. So we have I like cats like on the rows and I like cats like on the columns, and you'll see that if we take this for example, so the word vector for a row, and you add up all the values, they are going to sum to 1. That is equal to the total probability. So you can think of all of these items as a sort of probability now. Okay, so now we have a quite nice normalized similarity score. Now the meaning of this could be that of an attention score, because basically this matrix provides us information about the relevance of different parts of the sequence to each other. In other words, it gives us information for each word in relation to all the other words. So how relevant those other words are in relationship with the original, the target word. So this is an attention score because it's a relevant score. So how important are the different connections between words? Good. So this is step 3. Now it remains to be done only one final thing, and that would be step 4. So we take the attention score and we multiply that by the value matrix. Okay, so we multiply the attention score by the value matrix, and we are going to get basically the attention matrix Z, and this one is going to hold the relationship of each word with all the other words. Let me show you this step by step. So here we have the attention score, so the softmax of this matrix here. So we have the attention score. We multiply that by the value score here. And now we are going to get something interesting here. But before we get there, let me just add this notation. It's going to be very handy later on. So a word, like a vector here, a row vector here is going to be called V1, and so that's the vector associated with value I, so and that's value 1. Then we have V2 and V3. Okay, now I'm going to apply the multiplication there, and we're going to be getting this output here. So we've multiplied the attention score with the value matrix, and we get this result. And this is the attention matrix. So as you can see, the attention matrix has the same dimensionality as the value matrix here. So what it really means is that like we basically are applying the attention score to the value matrix, and we're going to get the overall attention matrix. Now, the attention score is going to bring to the table relevance. So how relevant the different words are for the different words in the sequence. And the value here, the value matrix, is going to bring information about the content, about the sequence. So when you combine those two by applying a multiplication, you're going to get a combined attention matrix that has information about the relevance as well as the content. So the content given by V, by the value, is going to be mediated by the relevance. I know this may be a little bit difficult to understand, but I'm going to give you 2 or 3 ways to understand it better. So the first one is a simple metaphor. Let's assume you are at a party. Okay, so you are at a party, it's very noisy, there are a lot of different people speaking. Okay, so the equivalent of this attention score, of this matrix here, would be your brain searching for people who are the most relevant to you. Okay, you are searching for them, but you don't know what they are talking about. Okay, so you just search for speakers you are interested in, but you don't know the content. Okay, and then the equivalent of this value matrix in this metaphor would be the content of those discussions. So the overall attention matrix that you get here would be the mediation of your brain kind of like searching for things that are relevant for you, for speakers that are relevant for you, and at the same time mediating that information with the content of the discussions that those different speakers are having. When you combine those two things together, you have the concept of attention here explained. Good. But now let's try to understand this from a slightly different angle. So I'm going to take this matrix, so the Z matrix here, and I'm going to rewrite it like this. So Z1 is going to be a vector, a row vector in this case, and it's basically this is the attention connected with the I word. For Z2, this is the attention for the like word, and Z3 is going to be the attention for the cats word. Now, we can rewrite Z1, in other words, like this guy here, this row vector, in a very compelling manner that is going to help us understand Z better. I've shrunk this equation up here, but we still have it as a reference, but I want to draw your attention down here to this new equation. The attention for I, so Z1, is equal to 0.7 times the value vector for I. So 0.7 comes from here, and V1 is this guy here, is this row vector here. And we sum to that this other multiplication, so 0.2, this value here, by V2, V2 being the value vector associated with like, and we do the same thing for the third element here. We can rewrite this like this, and it's going to become a little bit easier to follow. So this is equal to 0.7 multiplied by this vector I, that is V1 here, so 0.4 and 1 like this, and you can do the substitutions and see that that checks out. Okay, so in other words, in order to come up with the attention for I, we have the sum of the value vectors weighted by the scores, and these scores are associated with different words. So this 0.7 is associated with I, this 0.2 is associated with like, and this 0.1 is associated with cats. What does this mean? Well, it means that, for example, in the attention for I, in this vector, 70% of the information comes from I. 20% of the information comes from like, and only 10% of the information that makes it into this attention vector for I comes from cats. So this is like, it really goes back to that idea of relating each word to all the other words based on their relevance. Now you may be wondering, but why is this so important? And again, we're going to try to explain this from yet another angle, and that angle is going all the way back to the original sentence that we had and with the reference problem, and that was, my friends like tomatoes because they are tasty. Now, how can a transformer make sense of this phrase and understand that they is connected to tomatoes? Well, we just go in the attention matrix and we take a look at the attention vector associated with they, and it may look something like this. This is like completely made up, of course, but I just want to make a point here, right? So we have the sum of the value vectors associated with all the different words weighted by the relative weights. Okay, so let's take a look at the two main candidates they could be associated to. It could be tomatoes and friends, we said, right? And as you can see, friends has a score value of 0. So friends doesn't affect the attention vector of they at all. Rather, you have tomatoes with a score value of 90%, so 0.9. In other words, here we understand how powerful this attention mechanism is, because by looking at these attention vectors, we can see what these words, like in this case they, are related to in terms of other words. And in this case, it would be they is mainly related to tomatoes. And by having this formalization, a model like a transformer can actually understand long-term relationships. In this case, we have a very short sentence, but this can be applied to very long text or chapters even. And by using this attention mechanism, you can find the relationships between each word with all the other words out there. Isn't this just fantastic? It is. Now, one final angle I want to show you this from, and at this point we can say that we found a way of reconciling the intuition that we had, the visual intuition that we had of the self-attention mechanism with its formalization. In other words, this monster formula that we have here on the right-hand side and that we saw quite in detail is the formalization of this intuitive process that we've had, understanding how each word in the query connects to all the other items in the keys. So yeah, this is quite complex, but I think you should have a good understanding of it now, because we've gone through it quite slowly and step by step. Now, the question you may have, I'm quite sure, is, but why do we need step 4? In other words, why do we need to get the attention scores and multiply them by the value matrix? Couldn't just we use the attention scores directly? Well, no, and there's a reason. Because the attention score is all about relevance. Remember the metaphor that I've used. The attention score in a party is your brain searching speakers who are relevant to you, but you don't know anything about the content of those conversations. And indeed, that content is held by the V matrix, by the value matrix. So when you apply that dot product between the attention score and V, what you're going to get is a combination of relevance with content. Or another way of putting that is to weigh content by its relevance. That's why step 4 is fundamentally indispensable. Okay, you guys, so we are almost there with the self-attention. Well, actually, we are through it, and it's just fantastic news, but we want just to go through it through a quick recap. So, and this is a visual recap. We start from Q and K, we multiply those, of course we multiply K transpose with Q, and then we scale it, we scale the result, and that is a similarity score. Then we have a scaled similarity score. We apply softmax so that everything is nice and normalized. We can call this new construct attention scores, and then we apply a matrix multiplication between the attention scores and the value matrix, and as the output you're going to get Z, the overall attention metrics. That's the output of your self-attention mechanism. Quite complex, but quite rewarding, once you understand how it works. Okay, you guys, so that's fantastic news. Congrats, because as I mentioned when we started this section on self-attention, the moment you understand self-attention, you're halfway there, because once you understand self-attention, all the rest is going to be way easier, and this is also the key concept for transformer architectures. Wait, before we go ahead, I just want to mention that making this video is a huge effort, especially these long ones. So I would really appreciate it if you could give a like to this video if you're finding it useful, and also if you're not a subscriber of the Sound of AI channel, why don't you consider subscribing? It costs you nothing and it really helps this channel. Thanks a lot. Okay, you guys, so now we have all the information to go through all these different elements of the encoder block. And the first thing that we'll do is going through the multi-head attention. Now, this has become super simple now that we understand the attention mechanism, because a multi-head attention simply runs multiple instances of the self-attention mechanism in parallel. So rather than having a simple self-attention mechanism, you have many in parallel. Of course, this comes with quite the overhead in terms of number of matrices, because of course now each attention head is going to have its own Q, K, V, and Z matrices, not to count the weights for Q, K, and V. So each attention head is going to have its own number of independent matrices. And finally, once that self-attention mechanism is operated, is carried out, we're going to end up with a number of different attention matrices, one for each attention head that we have. So what should we do at that point? Well, that's quite straightforward. We take all of them, we concatenate them, and we just why not? We just multiply them by a weight matrix. But the basic idea is that you get all the outputs, all the attention matrices out of the parallel self-attention heads, and then you concatenate all of them and you get this big Z here. Good. I'm sure you may have another question is, but why multiple heads? Couldn't we just have a single head per encoder block? Again, you definitely can, but you're missing out if you're not using multiple heads. And the reason is because each attention head can focus on different parts of the input sequence. Perhaps there's a head that focuses mainly on syntax, another one on morphology, and a third one perhaps on semantics. So different heads can have different perspectives, different angles on the same sequence. And because of that, you can increase the complexity of the representation. So you can represent constructs that are more complex, and at the same time you also minimize the risk of overfitting because you're no longer fixating on a particular angle of that sequence, but rather you're looking at that sequence from different perspectives, from different angles. Good. Now let's go back to the difference between recurrent networks and transformers. There's something very important here. So we mentioned that LSTMs, or recurrent neural network, feed words sequentially. So you feed one word at a time into an LSTM. That is not true for a transformer because all the words are fed in parallel through the input embedding. And this is a great thing because everything works in parallel, and what this means is that we decrease the training time, learning is going to be way more efficient, and at the same time parallel processing is going to help learning long-term dependencies. And the reason is because you have the entire input in basically like in one batch, and so you have all the different words, and so your attention mechanism, your attention matrix is going to be able to capture all the relationship between each word with all the other words. And so it's fantastic. You can capture the long-term dependency there quite easily. But there's a problem. There's a terrifying problem there. And the problem is that transformer doesn't know anything about the order of your sentence, of your sequence. And I would argue that order is quite important in sequential data like music or text generation, isn't it? So we need to encode position or order somehow. Now, as I mentioned, the input matrix doesn't have order information. It doesn't know anything about order. And because this input embedding doesn't know anything about order, the transformer doesn't know anything about order at all. So our goal is that of finding a strategy to encode the order directly in the embeddings. And that strategy is called positional encoding. This is quite clever, so just stick with me. We get a matrix, we're going to call it P, positions, or PE, positional encoding. And this is going to have the same dimension as the input matrix I. So we have two matrices with the same dimension, and we are going to add them up, element by element. And then we're going to feed the sum of these two matrices to the encoder. Let me give you an example here. So here we have I, so that's the input embedding matrix, and this one carries semantic information. Of course, it carries all the information about the word, the words and the sequence, but it doesn't know anything about order. And here we have P. P knows nothing about content, about semantics, but it actually encodes positional information. So I provides content, P provides order. We add those two up and we get I prime. So I prime is a superimposition of information about semantics and positional information. So we have two types of information in the same matrix. And we feed this into the transformer. Now you may be wondering, but how can the transformer, who only says this output here, make up the difference or make up the two initial signals? So the original signal about semantic information and the other one about the relative positions. Well, it turns out that transformers can learn to interpret this combined signal quite easily, so they can make up the difference. So they can have like the combined signal, the combined matrix, and then make up the two signals and understand the content as well as the positions. Isn't that fantastic? But I'm sure you may be wondering, but how do we compute P? How do we compute this positional encoding? Well, I'm gonna laugh because this is quite something. Right, okay, yeah, so that is how we do the positional encoding. Now, let's go back there. It's not as difficult as it seems, but I mean, sines, cosines, what is that? Why is that? Well, we'll understand that in a second. So let's start with the first things first. These are like the formula that we're going to be using for creating this P matrix at different positions. So pos is the word position, and the word position obviously is the row index. So if pos is equal to 0, you are at row index 0, 1, 2, 3. Of course, I'm zero indexing here. Then we have I, and that is the embedding position. In other words, there we move over the column index. Okay, so what we say here is that we're going to be using the above formula here that uses sign for the even embedding positions or even column positions. And we know that these are even because it's 2i. Whenever we have at any row position, but only at even positions, we're going to be using this formula. And we're going to be using, for odd embedding positions or column positions, this bottom formula here with the cosine. And we see that this is the odd column position because it's 2i plus 1. That's an elegant way of referring to odd numbers. Okay, let's analyze one of this. So the only difference is that in the case of even positions we use sine, in the case of odd positions we use cosine. And it works like this. So we get like the position index, and then we have this 10,000, it could be 1,000, 10,000, whatever you want really. And you, to the power of 2i, I being the embedding position, the column position, divided by the dimension of the model. So this is the dimension of the model is the embedding dimension of the input embedding. So how many features we have in the input embedding matrix. I'm sure this is a bit shaky, so let's go through an example. I've parked these two formulas up here, so we'll have them as reference. And here we have the positional encoding matrix. We have a sentence with 4 words. Spaghetti monster is great. 1 word per row, and the different columns are the different features of the embedding for that particular word. Let's take a look at the row 0, column 0, and take a look at the value there. Okay, so here we use the sign function because that's an even index, column index, and so we're going to be using that, and we're going to take this function, and for pos we're going to put in 0, and for I we're going to put in 0 because these are both 0 indexes for both row and column. And we're going to be dividing by 3, and that's the dimensionality of the embedding. So of course we have 3 features in the embedding. Okay, so then Let's take another example. In this case, we are at row 0, but at column 1. So we need to take the odd, the cosine, because we are in an odd column index that's equal to 1. So the substitution here is also quite straightforward. The position is equal to 0 because we are at the 0 row, but I, in this case, is equal to 1 because the column index or the embedding position index is 1. Finally, here we are at cell 3, 2. So given we are at column index 2, that is even, so we're going to be using the sine function. So we substitute 3 here instead of pos, and then here for the I we go and substitute 2, that's the column index. So you get the idea. You are going to compile all of this positional encoding metrics by using these 2 versions of the same basic idea, depending on whether you are on a even or odd column index. Good. I'm sure once again you may be asking, but why do we use a sinusoidal function? Couldn't we use something else? Of course you could have used something else, but sines and cosines are very handy because you're going to get different frequencies for each position, and at the same time, sinusoidal signals help the model to learn the relative positions because a transformer can understand these sinusoidal signals quite well and separate them from the main input embedding, so that in the overall transformed embedding that has both the position and the content, the model is going to be able to separate the two. Good. So here we see a revised version of the encoder block. So now we start with I like cats. We generate an input embedding. That input embedding is added up with the positional encoding, and that information is fed into the first encoder block. Now, we are going to be looking at the next sublayer in the encoder block. We saw the multi-head attention. Now let's take a look at feedforward. This is possibly the simplest thing, the simplest layer that you can find in the entire transformer. This is really a simple, dense layer. Actually, it's most of the time it's 2 fully connected layers. They tend to process each data point separately, and by data point I mean each word. Each word embedding is going to be processed by itself independently of all the other data points out there. At each layer we're going to be using a nonlinear activation, and that's going to be ReLU, rectified linear unit, and by using ReLU we're going to add a nonlinear transformation to the data that increases its complexity. Why do we apply feedforward? Well, because feedforward has this nonlinearity, and this nonlinearity adds to the complexity of the overall representation that we can learn, so that we can learn more sophisticated features. Okay, now it remains only the final subcomponent to analyze, and that's the add and norm component. So let's analyze add first. Norm is associated to that, but let's focus on add first. So we have this first add and norm layer that connects the input of the attention layer to its output like this, and then we have a second add and norm layer after the feedforward sublayer, and this one connects the input of the feedforward layer to the output of the feedforward layer. If you're familiar with residual networks or residual convolutional networks, these are simple skip connections or residual connections, because they're called skip connections just because they skip one step and then they add the output of that subcomponent to its input? Well, we use this type of skip connections because they help mitigating a huge problem that we found in deep networks, and that is the problem of vanishing gradients. When you have a lot of layers, the problem is that the gradients tend to vanish. They become super small, and it's very difficult to continue training if you have small gradients, because you can't really optimize the moment those gradients vanish. So by using these skip connections, we help mitigating the problem of vanishing gradients. And then we have the norm part of this add and norm layer. So this norm part normalizes the data across all the features in the embedding for each position, for each word. Basically, we take the relative embedding and then we apply normalization so that we get a mean that's equal to 0 and the standard deviation that's equal to 1. We do that because with normalized data, there's going to be faster convergence, learning is going to be way easier, and this will happen because we prevent the values to change dramatically from one layer to another, and all of this is going to make convergence way faster. Okay, you guys, so we now have a very good understanding of the overall encoder block. I just want to give you the deeper meaning for each of these subcomponents. So the multi-head attention, as we saw, provides the overall context. It provides all these long-term relationships between each word with all the other words in the sequence. Then the feedforward layer provides nuance because it's able to add a degree of non-linearity that adds complexity and overall nuance to the types of representation that the model can learn. And finally, the add and norm layer is a utility layer, really. It's used simply for streamlining learning and make it easier with huge deep networks with a lot of encoder blocks stacked on top of each other. Fantastic. Let's go back to the original image of the encoder, as we can find it in the Attention is All You Need paper. By now, you should be able to understand all the different parts and know what they do. Let me go through all the processes that we have in the encoder step by step. So we start by creating an input embedding, then we sum the input matrix with a positional encoding matrix so that we have an input embedding now that also has some information regarding relative order. We feed this transformed input into the first encoder block and we compute the query, the key, and the value matrices by multiplying the input embedding with the relative weight matrices. At this point, we calculate the attention, the global attention, by concatenating the local attention matrices that are produced by different attention heads. Then we add the global attention to its input, to the input of the multi-head attention layer, and we normalize that. Then we take that and we feed that into the feedforward layer. The output of the feedforward layer is going to be added now to its input. So we apply a skip connection here. Again, we apply normalization. And at this point, we are at the end of the first encoder block. Remember, we can have as many encoder blocks as we want. In this case, in this image, we have n times, potentially n encoders. So we repeat for all the encoder blocks and we start repeating from number 3 in this list. And then once we are done, once we are at the last encoder block, we get the final representation R. This is extremely important because it's a very high-level representation that has a lot of abstract information, a lot of complex and contextual information. So it's very, very rich. That's the hope, at least, of the encoder. We take this representation and then we feed it as the input for the decoder. But we're not going to get into the decoder today because I think this video is already very, very long, and that's something that we're going to be addressing the next time. And this is what we're going to be addressing next time. It seems a little bit more than the encoder, but it is not, because the core of it, that is the positional encoding and the self-attention mechanism, is something that we've already covered. So we're going to bowl through the decoder, and then we're also going to take a look at how we can use the transformer in music generation more in general. Okay, before we go, let's wrap up this long lecture by taking a look at important points. Transformers are capable of capturing long-term dependencies, and that's what made them so successful and made them dominate so many different fields. They do have an encoder-decoder architecture. The magic happens thanks to the self-attention mechanism that creates relationships between all the words. We don't use for each encoder block a single attention mechanism, but rather we use multiple attention heads with the hope that they may capture different types of information, different perspectives on the same sequence. We do encode positions in the embeddings through the positional encoding strategy that utilizes this sinusoidal approach. We do have a feedforward layer in the encoder block, and that is used to add complexity, non-linearity to the model so that it can learn more complex representations. We also use an add and normalization facility to streamline the learning process. In the encoder, we may stack multiple encoder blocks with the hope to get ever more rich and ever more abstract representation of the original sequence data. And finally, the final representation that we get from the last encoder block is fed to the decoder. Oh boy, this was a long one, wasn't it? But I think by now you should have a very good understanding of the encoder side of the transformer. Next time we're going to be looking at the decoder component of the transformer, and we're going to be putting together encoder and decoder to see how the transformer works as a whole. We're also going to be looking at how we can use the transformer for music generation. That's all for today. I hope you found this video useful. I'll see you next time.